Preparing for a software engineering at Confluent interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Can you explain how Apache Kafka works? Kafka is a distributed log designed for durable, high-throughput event streaming. Producers write records to topic partitions, brokers store replicated partitions, and consumers read records using offsets. A consumer group divides partitions across its members, enabling parallel processing while preserving order within each partition. Replication improves availability, and retention lets consumers replay data. I would also mention that partition key selection determines distribution and ordering, which directly affects scalability and application correctness. While answering, focus on brokers, topics, partitions, producers, consumers, consumer groups, replication, offsets, and why Kafka provides scalable, durable, ordered event streaming rather than simply acting as a traditional message queue. Question 2. How would you design a highly scalable event streaming system? I would begin with workload assumptions: events per second, average size, peak traffic, retention, and acceptable latency. Then I would partition by a key that balances load while preserving required ordering, replicate data across availability zones, and scale consumers with partitions. I would define retry and dead letter behavior, monitor lag in broker health, and test rebalancing. Finally, I would clarify whether at least once delivery is sufficient, because stronger guarantees add complexity and cost. Make sure to cover throughput estimates, partitioning, replication, consumer parallelism, delivery semantics, retention, backpressure, failure recovery, observability, and the trade-offs between latency, durability, cost, and operational complexity. Question 3. What is the difference between at most once, at least once, and exactly once processing? At most once processing commits progress before work completes, so records may be lost but are not normally duplicated. At least once commits after successful processing, avoiding loss but allowing retries and duplicates. Exactly once means each logical result is reflected once, usually through idempotent producers, transactions, and coordinated offset commits. I would emphasize that exactly once is meaningful only across a defined boundary. External databases or APIs may still require idempotent keys. In your answer, distinguish loss from duplication, explain acknowledgement and offset timing, describe idempotent processing, and discuss why exactly once usually requires coordinated transactional behavior rather than a simple consumer configuration. Question 4. How would you choose a Kafka partition key? I choose a key based first on the ordering boundary. If account events must remain ordered, account ID is a natural key. I then test its distribution, because a popular customer can create a hot partition and limit throughput. The key should have enough cardinality to support parallelism, while remaining stable across event types. If requirements change, rekeying can disrupt ordering, so I would plan a migration strategy rather than changing it casually. Be sure to mention ordering requirements, cardinality, distribution, hot partitions, consumer parallelism, null key behavior, rekeying costs, and the business entity whose events must be processed sequentially. Question 5. What happens during a Kafka consumer group rebalance? A rebalance redistributes partitions when consumers join, leave, fail, or topic metadata changes. Under eager assignment, consumers may revoke all partitions before reassignment, temporarily pausing consumption. Cooperative protocols reduce disruption by moving only necessary partitions. I would minimize rebalances through stable membership, appropriate session and poll settings, and graceful shutdown. Before relinquishing a partition, the consumer should finish or safely checkpoint work, otherwise the replacement may process records again. Focus on partition ownership changes, consumer membership or metadata changes, stop the world effects, cooperative versus eager protocols, duplicate processing risks, and techniques for reducing rebalance frequency and recovery time. Question 6. How would you diagnose growing consumer lag? I would first compare production rate, consumption rate, and lag by partition rather than looking only at a group total. A single hot partition suggests key skew. Uniform lag may indicate insufficient consumer capacity or slow downstream work. I would inspect processing latency, rebalance events, broker request latency, errors, and resource utilization. Remediation could include optimizing handlers, increasing consumers up to partition count, adding partitions carefully, or applying backpressure and targeted scaling. While answering, cover whether lag is caused by producer spikes, slow processing, insufficient consumers, partition hotspots, downstream dependencies, rebalances, or broker problems, then describe metrics and remediation steps. Question 7. Design a URL shortener and discuss its trade-offs. I would expose a creation endpoint that validates the URL and returns a short identifier, plus a redirect endpoint for reads. A distributed ID generator or base encoded sequence avoids collisions. The mapping belongs in a replicated key value store. Because redirects are read-heavy, I would place a cache in front of storage and use expiration policies. I would also rate limit creation, validate destinations, protect analytics asynchronously, and define behavior when storage or cache nodes fail. Make sure to cover API contracts, identifier generation, storage, redirect latency, collision handling, expiration, caching, abuse controls, availability, analytics, and how read-heavy traffic changes the architecture. Question 8. How would you implement a thread-safe LRU cache? I would combine a hash map for constant time lookup with a doubly linked list ordered from most recently used to least recently used. Reads and writes move the accessed node to the front, while insertion beyond capacity removes the tail. For thread safety, I could use a lock around compound operations, or segment the cache when contention matters. Tests should cover eviction, updates, capacity 1, concurrent readers and writers, and exception safety. In your answer, describe the hash map and doubly linked list design. 1. Lookup and eviction, synchronization strategy, capacity handling, stale data concerns, and how you would test concurrent access. Question 9. What is backpressure, and how would you handle it in a streaming pipeline? Backpressure occurs when a downstream stage cannot process data as quickly as an upstream stage produces it. I prefer bounded buffers, explicit flow control, and measured concurrency rather than unlimited queues that eventually exhaust memory. Depending on business requirements, the system can slow producers, batch work, shed low-value traffic, or route failures to a durable retry topic. I would monitor queue depth and processing latency, because backpressure is useful only when its behavior is visible. Be sure to mention producer-consumer rate mismatch, bounded buffers, flow control, batching, throttling, queue growth, load shedding, retries, and protecting downstream systems instead of hiding overload with unlimited memory. Question 10. How would you design an idempotent event consumer? I would require each event to carry a stable unique ID and record processed IDs alongside the business update in one atomic transaction where possible. On retry, the consumer checks that record and returns safely if the event was already applied. For external side effects, I would use idempotent keys or an outbox pattern rather than relying on timing. I would also define deduplication retention, because permanent history may be expensive and late duplicates remain possible. Focus on duplicate causes, stable event identifiers, deduplication state, atomic business updates, retry behavior, retention limits, external side effects, and the difference between practical idempotency and universal exactly once execution. Question 11. Explain the outbox pattern and when you would use it. The outbox pattern solves the problem of updating a database and publishing an event without a distributed transaction. The application writes both business data and an outbox record in one local transaction. A relay or change data capture process publishes that record to Kafka and tracks progress. Publication may occur more than once, so consumers must be idempotent. It is especially useful when downstream systems need reliable notifications tied to committed database state. In your answer, connect database state and emitted events, explain the transactional outbox table, relay or CDC process, duplicate delivery, ordering, cleanup, and why consumers still need idempotency. Question 12. How would you design a schema evolution strategy for event-driven services? I would use a schema registry with compatibility checks and treat events as public contracts. Additive changes, such as optional fields with defaults, are generally safer than renaming or removing fields. I would deploy consumers that tolerate the new schema before changing producers, validate representative historical events, and monitor deserialization failures. For breaking changes, I would version the event or topic and migrate gradually. Compatibility rules should be enforced in C, not discovered in production. Make sure to discuss compatibility modes, optional fields, defaults, versioning, schema registries, producer and consumer rollout order, validation, deletion risks, and contracts that prevent silent data corruption. Question 13. What is the difference between stream processing and batch processing? Batch processing collects bounded data and optimizes for throughput, while stream processing handles records continuously with low latency. A fraud alert may need streaming decisions within seconds, whereas a monthly financial report can be calculated in batch. Streaming introduces state, windows, late events, and continuous failure handling. Batch simplifies completeness and reproducibility. I would choose based on freshness requirements, workload shape, and operational cost, and sometimes combine streaming ingestion with periodic batch reconciliation. While answering, compare latency, completeness, state management, replayability, cost, windowing, failure recovery, and appropriate use cases, while recognizing that modern platforms often combine both processing styles. Question 14. How do event time windows handle late arriving data? Event time processing uses the timestamp embedded in the record, so results reflect when an event occurred rather than when it arrived. Watermarks estimate how complete a window is, while an allowed lateness period keeps state open for delayed records. Late events can update or retract results, depending on the output contract. Longer waiting improves accuracy but increases state and latency, so I would choose thresholds based on observed delay distributions and business tolerance. Be sure to mention event time versus processing time, watermarks, allowed lateness, window types, state retention, corrections, and the trade-off between timely results and waiting for delayed events. Question 15. How would you debug a production incident in a distributed system? I start by defining customer impact, affected regions, error rates, and when the issue began. I check recent deployments and infrastructure changes, then correlate metrics, structured logs, traces, queue lag, and dependency health. I form a small number of testable hypotheses and prioritize mitigation, such as rollback, traffic reduction, or disabling a non-critical feature. After recovery, I confirm stability, identify the root cause, and document corrective actions without assigning blame. Focus on impact assessment, recent changes, logs, metrics, traces, hypothesis-driven investigation, mitigation before root cause, communication, rollback, and documenting preventative actions after recovery. Question 16. Tell me about a technically difficult project you owned. I would describe a project where I owned both the technical design and delivery, not just implementation. For example, I might explain migrating a high-volume pipeline, quantify throughput and latency improvements, and show how I evaluated compatibility, rollout, and rollback plans. I would be candid about a mistake, such as underestimating operational complexity, then explain the corrective action. The strongest ending connects the result to customer impact and a lesson I now apply. In your answer, use a clear situation task-action result structure, quantify scale or impact, explain your individual decisions, describe obstacles and collaboration, and show what you learned or would change. Question 17. How do you approach a coding problem during an interview? I first restate the problem and clarify inputs, outputs, constraints, and edge cases. Then I propose a straightforward approach, analyze its complexity, and improve it only if the constraints require optimization. While coding, I narrate invariants and keep interfaces simple. I test normal, boundary, empty, duplicate, and invalid cases aloud. If time is limited, I prioritize a correct, readable solution and explain how I would finish or optimize it. Make sure to cover clarifying assumptions, examples, brute force, constraints, complexity, clean implementation, edge cases, testing aloud, and communicating trade-offs before optimizing prematurely. Question 18. How would you improve the performance of a slow service? I would measure before changing code, starting with P50, P95, and P99 latency and tracing the request across dependencies. Profiling can reveal CPU hotspots, allocation pressure, lock contention, slow queries, or network waits. Depending on evidence, I might add an index, cache stable data, batch requests, reduce serialization, or adjust concurrency. I would benchmark with production-like traffic, compare error rates and resource usage, and keep a rollback path for regressions. In your answer, distinguish measurement from speculation, cover profiling, latency percentiles, CPU, memory, I/O, database queries, caching, concurrency, batching, and validating improvements with realistic workloads. Question 19. How would you make a distributed service highly available? High availability requires removing single points of failure across compute, storage, networking, and deployment. I would distribute replicas across availability zones, replicate critical state, use health checks and automated failover, and define recovery time and recovery point objectives. Timeouts, bounded retries with jitter, and circuit breakers prevent cascading failures. The service should degrade gracefully when optional dependencies fail. Finally, I would run fault injection and disaster recovery exercises to validate the design under realistic conditions. Be sure to mention redundancy, failure domains, replication, health checks, graceful degradation, timeouts, retries with jitter, circuit breakers, recovery objectives, and testing failures rather than assuming redundancy alone is sufficient. Question 20. Why do you want to work at Confluent? I am interested in Confluent because event streaming sits at the center of modern data architectures, and the engineering challenges are both deep and practical. Kafka requires careful thinking about durability, scale, compatibility, and failure recovery, which matches the systems work I enjoy. Confluent also combines open-source influence with customer-facing products and managed infrastructure. I would be excited to improve reliability and usability for teams building real-time applications at substantial scale. While answering, connect your experience to event streaming, distributed systems, open-source impact, customer scale, technical challenges, and Confluent's role in making Kafka and data in motion capabilities easier to operate and consume. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.